So let me finish this segment with some results for global linear models taken from McDonald's implementation of these type of models. So what I'm showing here is a table with dependency accuracy. So this is the proportion of dependencies that we propose that are actually correct. This is actually an evaluation measure we saw way back in the course. When we looked at lexicalized context-free grammars, we talked about evaluating the accuracy of a parser by looking at the number of dependencies it got correct. This model is a lexicalized PCFG that I developed for my PhD thesis. And of course, once we have a parse tree from a lexicalized PCFG, we can extract the dependencies from it using the methods I described earlier in this segment, and also the methods I described in the section on lexicalized PCFGs. And this model scores just over 91% in terms of dependency accuracy. Here are a couple of results from McDonald from 2005. The simple model that I just described gets close to 91% accuracy. And for a slightly richer model, which I'll talk about in a second, called a second order dependency model, we can get about 91.5% accuracy. So this is pretty impressive. The dependency parsing models actually are extremely competitive with lexicalized PCFGs in terms of recovering these dependency relations. And there are some very significant advantages of dependency parsing approaches. They are quite simple. It really is just a matter of defining these features that I just showed you, implementing dynamic programming, and then finally implementing the perceptron algorithm, for example, for parameter estimation. They're not only simple, but they're very efficient, as I'd said before. They are cubic time in the length of the sentence. And remember that for PCFGs, for example, the running time was cubic in the length of the sentence and also cubic in the number of symbols. So G is the number of non-terminals. And this term adds a lot. This could easily be 10 cubed or 20 cubed, 50 cubed, easily into the thousands. So dependency parsers can be significantly more efficient than a full PCFG parser. Let me just talk a little bit about extensions to what I've just described to you. There's been a lot of interest also in non-projective dependency structures. So actually defining gen to include these structures with the crossing dependencies. And for some languages, for example Czech, these kind of crossing dependencies are seen frequently, and so it's important to allow them. And that leads to a whole new research topic, which is how do we find the highest scoring non-projective structure. It turns out that dynamic programming doesn't really, actually dynamic programming can be employed in some cases, but there are also other interesting algorithms based on spanning tree algorithms, for example. Another very important extension is to look at second order and third order dependency parsing. What I mean by that is the following. So the feature vector representations I have shown you have looked at a single dependency at a time. So it looks at the single dependency in isolation from all of the other dependencies in the sentence. So we just look at this one dependency, and that's reflected because we have a local feature vector that looks at the sentence and just the identity of the head and the modifier in that particular dependency. In higher order dependency parsing, for example second order dependency parsing, we start to look at dependencies together. So we might actually have a feature which is sensitive to the fact that I have these two dependencies together in the parse tree, or maybe even these three dependencies together in the parse tree. So we can now have local feature vectors that maybe don't just look at the head and the modifier, but might also look at the grandparent. So maybe this is H, and this is H primed, and might also look at some other modifier, maybe this modifier here. So it's easy enough actually to extend the approaches I've described to allow local feature vectors that look at larger pieces of dependency structure. And this involves some complications to the dynamic programming algorithms that are used, but these models still remain tractable. With these kind of modifications, the state of the art is around 93 to 94%, at least on English Wall Street Journal data sets, in terms of recovering dependency annotations. And this really is a pretty impressive level of accuracy.